Hello children, welcome to the presentation of practical session. In this presentation, we are going to focus on the practicals types of reactions. These practicals are based on the topic of chapter 1 chemical reactions and equations. Types of reactions. First let us see for the aim. To perform and observe the following reactions and classify them into combination reaction, decomposition reaction, displacement reaction and double displacement reaction. Combination reaction. Theory. A reaction in which two or more substances combine to form a single product is called a combination reaction. A combination reaction can take place between two elements, two compounds, or between an element and a compound. Combination reactions are generally followed by the liberation of heat energy, that is, it is an exothermic reaction. In some cases, heat energy is required to initiate the chemical reaction. Examples: reaction between two elements, 2 Mg plus O2 gives you 2 MgO plus heat. Children, in this reaction, heat is required to initiate the reaction. Reaction between two compounds, CaO, calcium oxide, plus water gives you calcium hydroxide, as well as heat energy is liberated in this reaction. Materials required are a pair of tongs, beaker, quicklime, distilled water and a dropper. Good morning children. In our today's practicals, we are going to see for the types of reactions, standard 10. Okay, so in chapter 1, we have already studied for the theory, that is the different type of reactions, combination, decomposition, displacement and double displacement reactions. Let us see all these reactions one by one. So first, we will start with the combination reaction. Here I have calcium oxide with me, which is a white color powder, right? This calcium oxide, it is also termed as the quicklime. I will take this sample in a beaker. Children, calcium oxide solution is commonly used for whitewashing the walls. This is what we have learnt, isn't it? And when it comes in contact with carbon dioxide, it forms calcium carbonate, a white shiny layer. That calcium oxide I am taking, okay? To this, I will add water. I have taken distilled water. And slowly I go on adding. So you can see the fumes, children. You can see the fumes. It is an highly exothermic reaction. So you can hear the crackling sound. Bubbles are there. Children, here you can observe that the slake line, that is calcium hydroxide, settles at the bottom and a clear solution of slake line solution is formed at the top, which you also call it as the lime water. Now if I touch the beaker, it is slightly warm. That is, this reaction is exothermic in nature. Next reaction we will observe. But before that, can you write the reaction and show me for this reaction, children? Yes, CaO plus H2O gives you CaOH twice, where we observe two reactants combine to form a single product, and along with that heat is liberated, so it is an exothermic reaction. Let us see one more example for this combination reaction. So I have with me iron metal, okay, so we will be taking iron metal and sulfur powder. So in a test tube, I will add iron fillings. So there is black color iron fillings which I have taken in the test tube, right? To it I will add sulfur powder. With the help of the spatula. Sulfur is yellow in color, children. Just add it to it. Okay. And we'll make a mixture of it. by just simply shaking the test tube, you can observe that sulfur and iron has got completely mixed. Now let us heat this mixture. So for heating, I have the spirit lamp and the tongs with the help of which I will hold the test tube. Now children, whenever you heat a test tube, always see that you keep the contents away from your body. Okay? With complete precautions. Here I lit the spirit lamp. Now let us heat the mixture. We will keep on heating the mixture. Children, without heating, could I separate iron and sulfur separately? Yes, with the help of bar magnet we can do it, isn't it? Yes. Let us see what happens on heating. So children, you observe a black color compound is formed. This black color compound is nothing but ferrous sulfide. That is FeS is formed. So Fe plus S, that is iron plus sulfur, gives you FeS. Here also we observe that the two reactants combine to form a single product. So thus we can term it as a combination reaction. Now if I want to bring a bar magnet near it, will the iron fillings get separated? No. Why? Because a new compound is formed which has a new set of properties, and when two reactants combine to form a single product, it is termed as combination reaction. Earlier also we have seen for the burning of magnesium ribbon, where magnesium reacts with oxygen giving you magnesium oxide. So that is also an example of combination reaction. Observation. As soon as water is added the first time, the quicklime pieces crumple with a crackling noise, giving out steamy vapor. When more water is added, it forms a thick white suspension and starts boiling. After some time, a clear solution is seen at the top and a white mass that has settled at the bottom of the beaker. On touching the beaker, we find that it is very hot. Inference. Two compounds combine to form a single product. Hence, it is a combination reaction. Heat is liberated during this reaction and hence it is exothermic. Calcium oxide plus water gives calcium hydroxide plus heat energy is liberated. Slake lime, that is calcium hydroxide, settles at the bottom. The clear liquid that collects above the slake lime is calcium hydroxide solution, which is commonly referred to as lime water. Precautions. Do not handle quicklime with bare hands as it can cause burns on the skin. Use only borosilicate glass beaker while adding water to quicklime. This is because the reaction is highly exothermic and the beaker, if made of ordinary glass, can crack. So children, we had seen for the combination reaction. Now let us move for decomposition reaction. Theory. A reaction in which a chemical compound decomposes into two or more simpler products is called a decomposition reaction. Usually, decomposition takes place with the absorption of heat energy. Sometimes they may require electrical energy or sunlight also. These are called endothermic reactions. Examples: thermal decomposition. Lead nitrate, when on heating, gives lead oxide plus nitrogen dioxide plus oxygen. Ferrous sulfate on heating gives ferric oxide, sulfur dioxide and sulfur trioxide. Calcium carbonate on heating gives calcium oxide plus carbon dioxide gas. Electrolysis. Water is electrolyzed, that is, when electricity is passed through water, it splits up into hydrogen gas and oxygen gas. Sodium chloride, when electrolyzed, gives you sodium plus chlorine gas. Photolysis, when silver chloride or silver bromide are exposed to sunlight, then the process of photolysis takes place. Silver chloride on exposure to sunlight gives silver plus chlorine gas is liberated. Silver bromide on exposure to sunlight gives silver plus bromine gas is liberated. Materials required: boiling tube, test tube holder, Bunsen burner, blue litmus paper, red litmus paper, ferrous sulfate crystals. Children, next let us see for the decomposition reaction. For decomposition means to decompose, means to break down. To break down any substance, we will require energy. So, the energy which is given in the form of heat is termed as thermal decomposition. When the energy is given in the form of electricity, it is termed as electrolysis. And when the energy is given in the form of sunlight, it is termed as photolysis. Okay, so here we have taken an example of thermal decomposition for you. I have the sample ferrous sulfate. What is the formula for ferrous sulfate? FeSO4 dot 7H2. What is the 7H2O, children? Water of crystallization, isn't it? So this 7H2O is the fixed number of water molecules present in a unit salt termed as water of crystallization. So ferrous sulfate has got 7 water molecules. Let us see the color of this ferrous sulfate. Children, it's very important to observe the colors of the salts when you are using. Okay, see here, it is greenish in color. Right? Ferrous sulfate has a greenish color. So I will take it in a test tube. So a small sample of ferrous sulfate I have taken in the test tube. Always you should close the mouth of the samples which we are using so that we can prevent it from moisture. Now we will go for heating. For that I will just start the spirit lamp and we will heat it. When you are heating, children, always be careful that your heating a test tube should be away from your body, as well as see the way I have got the test tube in my hand. It's in a slanting position and the mouth of the test tube is away from my face, isn't it? It's very important to take precautions when you are heating it. See, a crackling sound has started. Slightly the color is being changing. The color is changing to reddish brown. Like you can say that chemical reaction is taking place. As there is change in the color, we have already learnt a chemical reaction is observed when there is a change in the color. So we had earlier ferrous sulfate green in color, now it is changing to brown. You can observe, children. Yes, you can even observe the water droplets which are settled on the inner walls of the test tube. From where has this water droplets come? That is the water of crystallization which was present in it, isn't it? 7 water molecules. Now when I heat it, these water molecules, they are evaporating and you can observe it. They are settled on the cooler part of the test tube. Here in the inner part you can observe there are minute water droplets. We will continue heating. Hear it carefully, children. There is a small crackling sound also it can be heard. So FeSO4, when it is heated, it breaks down into Fe2O3, that is ferric oxide, and that brown color is nothing but of the ferric oxide. Along with it, we will try to observe if anything is more added as a byproduct. Yes, see children, fumes, you can observe the fumes which are coming out, right? These fumes are of sulfur dioxide and sulfur trioxide. Now can you tell me what will be the nature of these gases? Nature. As sulfur is non-metal and it's in oxide form, so non-metallic oxides are acidic in nature. So if I bring a blue litmus near it, moist blue litmus paper near these gases, it will turn to red litmus. Let us do it and see. We will just hold it in the fumes. Can you see children? The blue litmus is turning to red. Yes, how beautifully the color is being changing slowly. So the fumes of sulfur dioxide and sulfur trioxide gases which are acidic in nature. So here you can observe children, see the blue litmus has turned red. On the lower part you can observe showing that non-metallic oxides are acidic in nature, as well as this evolution of the sulfur dioxide and sulfur trioxide gases. So when ferrous sulfate, that is FeSO4, is heated, you get ferric oxide, that is Fe2O3, plus sulfur dioxide and sulfur trioxide gases evolved. So this is an example of decomposition reaction. So here we have used heat, so it is termed as thermal decomposition. And as this chemical reaction requires the presence of energy, it is an endothermic reaction.
Observations. When the boiling tube is heated strongly, the light green ferrous sulfate crystals crumple to form a white powdery mass and give off a colorless gas. This white powdery mass then slowly changes to reddish brown color. When the gas is gently wafted towards the nose, it smells like burning sulfur and causes a coughing sensation. When the gas is tested with a moist blue litmus paper, the color of the litmus paper changes to red. When the gas is tested with a moist red litmus paper, the color of the litmus paper does not change. Inference. Heating ferrous sulfate crystals strongly is a decomposition reaction because a single chemical compound, ferrous sulfate, break into three simpler substances: ferric oxide, sulfur dioxide and sulfur trioxide. It is an endothermic reaction as it proceeds with the absorption of heat energy. Precautions. While heating ferrous sulfate crystals, use a dry clean boiling tube. Ensure that the water droplets do not flow back into the boiling tube during initial heating. Do not keep your nose close to the boiling tube to smell the gas coming out. Just waft them outwards your nose and smell. Sulfur dioxide is a poisonous. Therefore, once the experiment is over, place the boiling tube used outside the laboratory in the open. Displacement reaction. Theory. When a more reactive element displaces a less reactive element from its salt solution, it is called a displacement reaction. Example. Copper sulfate plus iron gives ferrous sulfate plus copper. Here, iron is more reactive than copper and so is capable of displacing the copper from its salt solution. Materials required: test tube, 2 iron nails, thin wire, copper sulfate solution, laboratory stand.
Next, let us see for the displacement reaction, children. For displacement reaction, we need to know few things, that is the metal reactivity series. But how are the metals arranged in the metal reactivity series? Let us understand this with the help of these reactions. Okay. So I have over here copper sulfate. Formula is CuSO4. Again, this salt also contains water of crystallization, that is 5 water molecules. So we write it as CuSO4.5H2. Okay. And I have iron metal with me. Right. Let us observe. So this is a beaker and I am pouring water in it to make the solution of copper sulfate. So I have copper sulfate solution. You know, children, copper sulfate is blue in color, a beautiful blue color salt, and this color is because of the 5 water molecules present in it. Okay, so here I add the sample of copper sulfate to it, and with the help of a glass rod, I will just mix the solution. And completely dissolve the copper sulfate in it. You can observe that the copper sulfate has got completely dissolved in a blue color solution. To this, I can add an iron rod, that is an iron nail, or I can add iron fillings also. Okay, so I will add iron fillings first, that is the small pieces of iron metal. Right, I'll make one more solution in which we will even dip the iron rod also and see. So you can observe for both the cases. So I'll again make a solution of copper sulfate. Observe a beautiful blue color salt. I just mix it and dissolve the complete copper sulfate in it. In this manner, with the help of the glass rod, children. So here there is a copper sulfate solution ready. This is the iron nail, and I'll just dip the iron nail and we will see wait for the reaction to take place. Okay, here already we had added iron fillings. Let us see. Can you observe, children? Slightly the color is changing, isn't it? Observe blue and this is greenish. Here you can observe the blue color solution is now fading and it is turning to green in color. Beautiful reaction. What is this green color solution, children? This is ferrous sulfate, that is FeSO4 is being formed, and you can observe at the bottom red color copper is set free. Now why did this reaction take place? See, so beautifully you can observe it, children. First it was blue in color, now it is turning to green. Even this reaction will take place and we will wait for the reactions. Okay, so this FeSO4 is formed over here. We can say that iron metal was more reactive than copper, so it could displace copper from its salt solution. So we have a reaction CuSO4 plus Fe giving you FeSO4 plus Cu, that is copper is set free, which we observe as a red color coat at the bottom. This is the copper which is set free and the solution formed is of ferrous sulfate, right? So a beautiful reaction. Even this reaction, this iron also will react with the copper sulfate solution and get a coat. We will see. And children, this displacement reactions are little slow reactions, and that is why it is taking little time. So now in this experiment, we concluded that iron metal is more reactive than copper. Let us do it vice versa and see. That is, let me make a solution of ferrous sulfate. So here I have, children, ferrous sulfate which is green in color. So I'll take a sample of it, ferrous sulfate salt. Here I have taken the salt sample in it and let me mix it with the glass rod. Children, you may have a question that here we have ferrous sulfate green, here we are having ferrous sulfate as yellowish brown. So children, it undergoes oxidation very quickly when it comes in contact, right? with the air, and so you can observe that its color is yellowish brown. Now, if I put a copper metal to it, I have added a copper metal to it, and let's see if there is any change. Do you observe any change? No, there is no change observed over there, isn't it? Children, let us observe the reaction where we had added iron nail to it. So you can see over here, the red color coat has started forming on the iron. A red color coat. Can you observe, children? This is nothing but the copper which is being displaced from the copper sulfate solution by iron nail. And slowly this color change will be observed in the solution also. So we will, if you keep it for more longer time, you will observe the similar reaction. So for showing you the fast reaction, I have used iron fillings, which is observed here. Even here, the same color will change. That is, the blue will change to green. And children, I know you must have understood now very well that why there is a difference in these two colors. You can observe that ferrous sulfate crystals, when I have added in the water, it has come with the contact with the air and it loses its water molecules, 7 water molecules, and showing a drastic change due to the process of oxidation. So this shows that copper metal is less reactive than iron, so it could not displace the iron from its salt solution. And thus we can say that iron metal is more reactive than copper. In the similar manner, children, there are various reactions taking place, or experimentally it has been proved for the metal reactivity series.
Observations. At the start of the experiment, copper sulfate solution is blue in color and the nail is silvery grey in color. After half an hour of immersing in copper sulfate solution, the surface of the iron nail can be seen covered with a deposit of brick red colored substance. The color of the solution in the test tube has turned much lighter when compared to the original copper sulfate solution, and a greenish color solution is observed. Inference. The reaction between iron and copper sulfate solution is a displacement reaction. In this reaction, the more reactive metal, that is iron, displaces the least reactive metal, that is copper, from its salt solution, that is copper sulfate. The chemical reaction is represented as follows. Copper sulfate plus iron gives iron sulfate plus copper. Precautions. Copper sulfate solution should be prepared in distilled water. Ensure that it is not a concentrated solution. Ensure that the iron nails are clean. If not, use sandpaper to clean their surface. Double displacement reaction theory. When two compounds react to form two new compounds, interchanging their ions, it is called a double displacement reaction. Most often, this is a neutralization reaction. But when a precipitate is formed, it is termed as a precipitation reaction. Example, barium chloride plus sodium sulfate gives sodium chloride plus barium sulfate. Materials required: 4 test tubes, droppers, sodium sulfate solution, barium chloride solution, dilute nitric acid and dilute sulfuric acid.
Our next reaction, children, is the double displacement reaction. Let us take an example over here for the double displacement with sodium sulfate and barium chloride. Children, as we have learned in double displacement reactions, there is exchange of ions taking place between them, and we observe a precipitate which is formed in this kind of reaction. So it is also termed as a precipitation reaction. So what is a precipitate? It is an insoluble substance which is formed in the products, isn't it? Let us observe this with the help of an example, that is perform the practicals. Here I have sodium sulfate for you, and it is a white color amorphous salt. I take this in a test tube. So a small sample of sodium sulfate, and we'll make a solution of it. So I will add water to it and just shake it very well. it gets very easily dissolved in the water. So I have the sodium sulfate solution ready over here. So I'll keep it here. Other one, I have barium chloride. Can you observe, children? This is the barium chloride salt. I'll show you the color of it. It is a crystalline white color salt, barium chloride. I'll take it in the test tube. And even again make a solution of it. Completely dissolve this barium chloride in the water by simply shaking it. Now, when I add this barium chloride solution to sodium sulfate, let's observe what happens. Here, a white color solution is formed, and this white precipitate insoluble substance formed is nothing but the barium sulfate. So, a white precipitate of barium sulfate is formed along with sodium chloride. Now, how do I identify the barium sulfate and sodium chloride formed? For that, I will keep the solution for a while and observe it. So, after some time, we will observe for the difference in these two, where the barium sulfate settles at the bottom as it is an insoluble substance, a precipitate has formed, and the sodium chloride, a clear solution which is seen at the top. So, children, after keeping for some while, you can observe the two layers very clearly. So, the barium sulfate which is insoluble has settled at the bottom, and the sodium chloride which is forming a clear solution you can see at the top of it. So, we can say that the barium sulfate white color precipitate is formed in this chemical reaction. So, this was an example for your double displacement reactions. So, children, let us see one more reaction for the double displacement reaction. So, I have lead nitrate and potassium iodide. Now, children, you can observe that this lead nitrate salt is kept in the colored bottle. Why it must be so? Yes, because it decomposes when it comes in contact with the air. So, it is kept inside the colored bottle to prevent the exposure of the salt directly to the light. Okay. Now, we are going to make the solution of these two, of lead nitrate and potassium iodide. See here. I'll take a sample of lead nitrate. Observe the color, children. It is white crystalline salt. So, I will make a solution of it. And immediately you should close the bottle and keep. Right? So, let's dissolve it. And I have to make the solution of potassium iodide. So, this is potassium iodide. Take a sample of it. Children, it's the white crystalline salt. Okay? So, just make the solution of it. So, I have the two solutions. One is lead nitrate and potassium iodide solutions ready. We will simply add these two and observe for the reaction. What do you observe, children? A beautiful yellow color precipitate of lead iodide is formed along with potassium nitrate. So, this is a double displacement reaction where a yellow precipitate of lead iodide is formed.
Observations. As soon as the drops of barium chloride mix with the sodium sulfate solution, the solution becomes white in color. On adding more barium chloride solution, a thick white precipitate does not dissolve. On adding dilute nitric acid or dilute hydrochloric acid or dilute sulfuric acid, the white precipitate does not dissolve. Inference.
The chemical reaction between the sodium sulfate and barium chloride is a double displacement reaction. The ions of two different salt solutions exchange to form two new salts. The chemical reactions can be represented as sodium sulfate plus barium chloride giving sodium chloride plus a white precipitate of barium sulfate. Barium sulfate is insoluble in dilute nitric acid, dilute hydrochloric acid and dilute sulfuric acid. Precautions. Do not fill more than 1/3 of the test tube with sodium sulfate solution. Add barium chloride slowly by shaking the test tube continuously. So children, I hope you must have understood all the 4 reactions through the practicals. Thank you so much.